So, looking at heat capacity and at specific heat capacity, I thought I would start with heat capacity to draw the distinction between that and specific. So heat capacity would be the energy required to raise the temperature of an object by 1 degree C. So you might talk about the heat capacity of a mug or the heat capacity of a saucepan, but that's very specific, if you'll excuse the use of the word, to that object. It doesn't give us any indication of the usefulness of the material. You could have a big mug and a small mug, and you'd have no indication of the usefulness of the material. If one mug was made of steel and the other one was made of ceramic, it wouldn't help you decide which was better, steel or ceramic, for making that mug. So the specific heat capacity is the one you need to know, actually. The energy required to raise the temperature of 1 kilogram, that's the bit that makes it specific, of a material by 1 degree C. And just to be really tight on this, that has to happen without change of state. You might say, well, so what? How does that change things? Well, if you were raising the temperature of ice from -1 degrees to +1 degrees, you would have the energy required to raise the temperature of the ice from -1 to 0 and to raise the temperature of the water from 0 to 1, but you would also have the energy required to change the ice from ice into water. So there'd be more energy required to raise the temperature by those 2 degrees than if it was either ice or water, but not changing. So that's the reason for the without change of state. Now, in terms of uses of this, generally speaking, something with a low specific heat capacity, the symbol is C, is a conductor. So this is something which takes less energy to raise the temperature and also loses the energy more quickly because it's a conductor. So it heats up more quickly and it cools down more quickly. An insulator, well, that takes more energy. Now this, a saucepan would be a good example there. Takes more energy to raise the temperature, and it loses the energy more slowly. So here, maybe a storage heater where you heat up maybe 120 kilograms of concrete using an electrical heater, and although it takes a long time and a lot of energy to heat that up, it holds that energy really well and you can release it over time. Now what I haven't done here is the equation, and I should have done that. So let's look at the equation. The energy required to raise the mass, m kilograms, by a certain amount of temperature for a material specific heat capacity C, that is the equation you need to use. So of course, if you doubled the mass, you would double the amount of energy required. If you doubled the change in temperature, you would double the amount of energy required. And as you change C, you will of course also change the energy required. So it makes sense. If it takes, for example, with water, it takes 4,200 joules to raise the temperature of 1 kilogram by 1 degree C. These are the units of specific heat capacity. So if I wanted to raise the temperature of, let's say, 1 kilogram from 20 degrees C to 100 degrees C, I would have 1 times 4,200 times that change in temperature, which is 100 minus 20, 80 degrees. So that's how you work it out. So that's what specific heat capacity is, the symbol for it, the equation we use to work it out, an example of how you might use it, general principles of low specific heat capacity being conductors and high specific heat capacity being insulators, the implications of that. If it's a conductor at low specific heat capacity, it will take less energy to raise the temperature, but then it will lose it faster as well. So with your saucepan, you don't want a saucepan that stores a huge amount of energy in it when you heat it up, so it takes longer to heat, and then that energy is stored in the saucepan. So you imagine making your saucepan out of concrete. The saucepan will take a long time to heat up. It will then cook your food, but it will have a huge amount of energy stored in it. So it'll stay hot for a very long time, or it'll vaporize a lot of water when you put it into the sink to wash it. That's not good. Whereas if you make your saucepan out of aluminium, it has a small specific heat capacity aluminium, so it will heat up quickly, it will cool down quickly, and the pan itself will store less energy. You don't want the pan to store it, you want the pan to deliver it to the contents of the pan. Whereas with an insulator, it has a high specific heat capacity, so it takes more energy to raise the temperature, it will lose the energy more slowly, so you can store energy in that. And water, quite a high specific heat capacity, it's an insulator, and water stores a lot of energy. So even though the temperature of the water around the UK is quite low, there's a lot of energy in there, and that energy helps to keep the UK warmer than, say, Siberia, which is on the same latitude. So that's why we are warmer than Siberia on the same latitude, because we have that North Atlantic drift keeping the UK warmer. You have this current of relatively warm water keeping the UK warmer. So although the temperature is quite low, you know, if you got into the North Sea, you think it was pretty cold, but because the temperature, the energy is stored in the water, it takes a lot of energy to raise the temperature of the water, and there's a lot of water, then that energy keeps the land warmer. So that's my introduction. Now, in terms of the experiment you need to know, you took a block of material, and I haven't labelled that, my apologies for that, but you took a block of material, 1 kilogram of aluminium or iron or steel. You wrapped it up in some insulation to reduce the thermal energy loss from it. You had a temperature probe to measure the temperature. You had an immersion heater connected to a circuit where you measured the current and the PD across the heater, and a stopwatch to measure the time. So that was your setup. And what we did then, we recorded, let me do that in black. We record the starting temperature, and the temperature, the maximum temperature after the heater has been on for 5 minutes, which of course is 300 seconds. We record the PD across the heater in volts. We record the current through the heater in amps. We turn off the heater after 5 minutes and wait until the temperature stops rising. Now, if I take you back to the diagram there, you can see that you're supplying the heat at this point and you're measuring the temperature at this point. So after 5 minutes and you've turned the heater off, some of the thermal energy you've supplied hasn't got as far as the temperature probe yet. So you have to wait until the temperature measurement stops rising, and then you know the maximum temperature rise. So that's what you do, that's what you record. And the block is wrapped in insulation to reduce, not to stop, but to reduce thermal energy loss. So that's what we do. Let's look then at the analysis of the results. So we have a starting temperature, let's call that starting temperature, and we have a final temperature after the thing's been on, the heater's been on for 5 minutes. We have a potential difference across it, let's say that's 12 volts, and we have a current running through it, let's say that's 4 amps. It's probably nearer to 3 amps, but we'll call it 4 for now. So what we do is we say the energy supplied, of course, is from the heater, and that is the power times the time, of course, and the power is V times I, or I times V. So we had 12 for the PD times 4 for the current times, well, the time has to be in seconds, right? So it's 300. So you've got 48 times 300 joules supplied, which gives you 14,400 joules. And that energy is the mass times the specific heat capacity times the change in temperature. So let's say that is 20 degrees, and let's say that is 40 degrees. Now we will have measured the mass of this using our balance, and we'll have found that was 1 kilogram, because our samples always are, times the specific heat capacity we're trying to find out, times the change in temperature. Well, that's 40 minus 20. 20 is 14,400. So if we divide our 14,400 by 20, that will give us our specific heat capacity. Now 14,400 divided by 2 is 7,200, so that's 720 joules per kilogram degrees C. Now, is that a good value? What are the issues with that? Well, if we go back and look at our diagram, we have supplied 14,400 joules from this circuit to here. What has that 14,400 joules done? Well, it heated the heater. There's the first thing it did. That doesn't change the temperature of the block initially, that changes the temperature of the heater. So some of the energy we supplied went to heating the heater. Some of the energy went to heating the temperature probe or the thermometer. So whilst we are saying 14,400 joules went into our block of material, actually it didn't. Some of it went to heating the heater. Some of it went to heating the data logger, or the temperature probe rather. The rest of it went into the heater. But did it stay there? No. We've wrapped it in insulation in order to reduce the energy loss, but some of the energy is going to leave the block. So some of the energy that we have supplied from here has gone to the data logger rather than the block, the data logger rather than the block, to the heater rather than the block, and then has left the block. Some of it has gone to the block and left the block again. So all of these factors mean that the amount of energy we say we have supplied is greater than the energy we have actually supplied. So let's look at the implications of that. Let's get rid of my labels. So this figure, if we look at our equation, this is too big. This figure too big. Some energy went to heating the heater. Some of it went to heating the probe or the thermometer, depending on what you're using. Some of it was lost from the block. Now we've done what we can to prevent that loss, but it has been lost, some of it. Okay, so this figure is too big. which means this figure is too big, or if you like, this figure is too small, which means this is bigger than the true value.